we're going to look at directional derivatives and maximum rate of change. I'm also going to talk about, I think, a practical example, and then call it good. So we all know the formula for directional derivative. If I didn't mention it, shall I mention something right now? The direction of the derivative, right? Which is typically called u. You know, something like that. This needs to be a unit vector. In almost every question that we've done, it's been a unit vector. So if I forgot to mention that, I've now mentioned it to you. So what happens then if it's not a unit vector? So let's do a pretend version of that question. And I'll do a messy one that's got a lot of things in it. So suppose that we're given our usual function, and I won't make it particularly awkward. Right, I'll have it, say that guy. And we're interested in its directional derivative at the point 1, 1. And the direction that we're going to go is 3, -4. Well, the first thing I need to do is I need to convert this fella into a unit vector. So the magnitude of this vector is 3 squared plus -4 squared, which is 9 plus 16, which I've chosen quite nicely to be that. So that when we use our vector, I guess I'm going to have to just call it u again. We are going to use that vector. Now, would you agree it's in the same direction as the original? It's just 1 unit long. That's just a little nuance. A lot of the questions we've done are, remember the ones where it said theta was pi/4? Remember those ones? They were unit vectors because cosine pi/4, sine pi/4 is 1 unit long. So back to our fella.
Professor?
Yes.
I think there's somebody in your waiting room.
Oh, thank you. Thank you. We got it. Let me click on it again. Ah! Just sent them a message. I didn't mean to. Right. Okay, so our gradient vector is what it always was, 2x plus y and what? X plus 5. So we want to get the direction vector. It's going to be that guy, dot product with this guy. So I'm going to do it at the point 1, 1. So that's going to be 3. That's going to be 6. And this fella's going to be 3/5 and -4/15. So what's that going to get me? What am I saying, 4/15? That's just 4/5. I can't read one right. 3 times 3 is 9/5. Take away, oh good, I finally got one. I finally got a negative answer. Take 9 away from that. What do we get if you take 9 away from that? Let's see. We get, oh, I wasn't expecting a nice answer, but I did. So on this surface, at the point 1, 1 on the floor, if you went up to the surface and then you headed in the direction of 3, -4, using the unit vector to represent that same direction, you would be going downhill with a slope of 3. So that is the kind of little piece of directional derivative that the adaptation that you will do if the direction is not a unit vector. Now, let's do a maximum rate of change question. And then do an application. Let's do it. Let's do this fella. I'm going to pause for a second and add someone else who just arrived. And there we go. And go back in. Right. picking a really, really simple surface. You recognize this is actually a fourth dimensional surface. When you do f of xy equals x squared plus y squared, that kind of thing, it's technically a three-dimensional surface, right? Because that counts as a variable as well. That guy there, I believe, looks like this. It looks like a big mound. This here would be a fourth dimensional version of that. I can't think in 4 dimensions, I just can't see it. But our question is, at the point 1, 2, 3, what is the maximum derivative, right? So we've been asked to find the maximum directional derivative at that point, right? Well, in this case, you find that guy. 2x, 2y, 2z. I'm making my life easy. The gradient vector at the point 1, 2, 3 is 2 lots of 1, 2 lots of 2, 2 lots of 3. And the answer is, what is the maximum directional derivative? What they're asking for is what's the value of it. And the cool thing is that it is the magnitude of this fella. So the maximum is the magnitude of the gradient vector. So in this case, what would that be? That would be 2 squared is 4, 4 squared is 16, 6 squared is 36. Looks like the square root of 56. Question?
Yeah, so about the maximum directional derivative, which is the magnitude of the gradient vector. Well, then again, is directional derivative is the gradient times the vector, the unit vector. So wouldn't that be the gradient times the gradient? Like that's the gradient squared. So how is that the square? How is that the magnitude of the gradient? That's just the gradient squared. Like directional derivative.
If you find the magnitude of a vector, isn't the magnitude of the vector the square root of its components squared and added?
Sorry, I still don't understand how that, like,
Okay, let's pretend that this was not a gradient vector. It was just any old vector in the universe. If I said I had a vector and its components were 1, 2, 3, what is, I'll put double lines around it. That might help. What is the magnitude of this vector? Well, the formula for getting the magnitude of any vector is 1 squared plus 2 squared plus 3 squared. In this case, the magnitude of this vector would be the square root of 14. What the theory tells us is that we're finding the maximum value of the directional derivative. Maybe I should have phrased it a bit cleaner. So this is, the theory says that the length of the gradient vector at that given point, whatever that length of that vector is, that will be the maximum value that the directional derivative will take. And so it's just a theory that tells us. So I find out what it's equal to in terms of numbers. And then I just find the magnitude of this vector, which is this guy.
Mr. Robertson, never mind. Yes. I found out the math myself. So first you have to convert the vector and the direction vector into a unit vector. So basically like you find the magnitude of it and then you divide each of the components by it, then you multiply it by the gradient. So yeah.
It works out?
Yes. Yeah.
Oh, it's much better if you figure out yourself then. That is cool. Now, this here represents the largest slope that you could get on this surface at that point. So imagine being at that point and just looking around like a clock, all the directions I could go. The steepest I could go would be this guy. And I just realized, isn't this guy simplifiable?
It's 2 root 14.
Yeah. But I mean, that's just a minor thing. Now, the second part of that question could simply be, and what is the direction that you should go to achieve this maximum derivative, right? And that guy is basically this fella, right? That's the direction that the vector should go. But we typically turn it into a unit vector. So it will be 2 over the square root of 56, 4 over the square root of 56, and 6 over the square root of 56. And then we would try and at least attempt to simplify it. And I would cancel out some 2's, and I'd look at something that looks like this. So this would be a unit vector in the same direction as that. Now, when I was looking at WebAssign, it looks like they will allow that as the correct answer. They will allow the unit version. So that guy and that guy are the same direction. Isn't this guy just not a unit vector and this is? And if you really want to be really nitpicky, wouldn't that guy also be the correct answer? I mean, that guy is just to simplify by rationalizing the denominator. So we have where do we go with this? We have a large number of different versions of the correct answer to what direction you should go. Thankfully, there's only really one answer to what's the magnitude of the directional derivative, right? What number would it be? Are we cool with that process then? So if you get a question that says, find the maximum directional derivative in what direction is that vector, you're looking for this guy and one of these vectors here, or that vector. Okay, let's do a practical one. Not my favorite, but you are engineers, so you do want to do practical things. So the temperature in a three-dimensional object at coordinates x, y, z, its temperature is given by 10 e to the power, and I'm picking my own version of this, that guy. So can you imagine if you wanted to know what the temperature is, probably in degrees Kelvin, at the point 1, 2, 3, it would be whatever the value of 10 e to the negative x squared minus y squared minus z squared is. So far, so good. And we are going to find in question A, they call it, this is how they phrase it, the rate of change of the temperature at the point, it doesn't matter what the point is, does it? 1, 2, 3. In the direction towards the point 2, 4, 1. Well, when you do practical questions, they sometimes phrase things differently. The rate of change of temperature is basically saying find the directional derivative. You're starting at this point and you're finishing at that point. Won't that be the direction that you're talking about then? So I want to find the vector, I'll call it V, who goes from the point 1, 2, 3 towards the point 2, 4, 1. And so second takeaway first, second takeaway first, second takeaway first. That's the vector that I've got. So far, so good. Now, if I want to do the directional derivative, let's just find out who the unit vector is. I'm going to do it in my head. What is the magnitude of this vector? You should be able to do numbers in your head. What's the magnitude of V?
3. 3.
Root, how much?
3, right?
Square root of 5.
Because
Yeah, square root
2
of 5.
squared is 4, and yeah, there's 2 of those.
Okay. So that's what you're saying, yes?
Well, now you've got me questioning myself.
Oh, it's 3.
Well, okay, let's put it in.
It's
Square root 1 squared, 2 squared, negative 2 squared, right?
Yes.
1, 4, and 4, 9, 3. The reason you threw me there is that I didn't realize it was going to simplify. I was expecting the 9, not the 3, because that's me. I'm just not very aware. So won't the unit vector then just be 1/3, 2/3, negative 2/3? Okay, we are about ready to evaluate the directional derivative. Let's see what I need to find. I need to find this fella. Would you agree that this question involves us finding 3 different partial derivatives? And I guess I should call that t, shouldn't I? Because that's the variable. In this case, it's a t. I need to find these 3 guys, right? Is this function symmetric?
Yeah.
So if I find the answer to x, can't I just use that to figure out the other 2 without doing everything from scratch? So if you do this fella, you will get, with respect to x, you will get 10 e to the ugly guy, and then won't you get a times negative 2x? Because the partial derivative of this with respect to x is just negative 2x. So that means you get negative 20x e to the negative x squared, negative y squared, negative z squared. You comfortable with where the negative 20 came from? Jason, you look puzzled. Okay, we're good. Right, tell me what the next one's going to be without doing all that work, just using this as my template.
Negative 20y.
Agreed. I got 3 people all at the same time, which is a good sign. I'll do the next one then. Might as well make it green because I can. If you can't read all my, because I'm crunching this, isn't this guy the same guy every time? So the gradient vector at the point 1, 2, 3 becomes negative 20 times 1 e to the power of 1, 2, and 3. So it's 9, 10, 14. So that's e to the negative 14. The next one is negative 20 times 2 e to the negative 14. And the third one is going to be negative 20 times 3 e to the negative 14. So what do we get? We get negative 20 e to the negative 14, negative 40 e to the negative 14, and finally negative 60 e to the negative 14. I think that's one of the reasons I don't like practical questions, because they're never pretty. Aren't they just clunky and ugly looking? Because in real life, that's kind of what numbers are. They're not, you don't get 2, don't you always get some really ugly thing, whatever it is. But we got it. Okay, so directional derivative of this particular function at the point 1, 2, 3 is going to be the dot product of the gradient vector with u. So it's going to be, I'm just going to call this guy dot, 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 because I don't want to have to write this again, with a 1/3 a 2/3, and a negative 2/3. And I'm going to dot, dot, dot that entire mess now. But essentially, won't I take this guy, times it by a third, take this guy, times it by 2/3, and take this guy and multiply it by negative 2/3. And when I put the whole mess together, won't I just get a big chunk of e to the negative 14s? I don't know how many it is. It's 87.2 of them, or 49/312 of them, or whatever. But that's as much as I want to do on that. It's a bit cruel, isn't it, that I just do that? Do you know the engineer people amongst you? That's the one they want to get to grips with. They want to see what this number is, because maybe it'll mean something to them. Yeah. Okay, I'm calling it good. Anything about that question? Apart from the fact it's downright ugly, it's still the same process, find the directional derivative. Oh, if I wanted to find the maximum temperature gradient, right, the maximum increase or decrease in temperature, wouldn't I just find this fella at that point, and its magnitude would be the maximum derivative, right, the maximum rate of change. So where are we off to next then? Well, it's been a while since you've done this kind of question. How to find local maximums, minimums, and saddle points of a 3D surface. So this is going to be what the next section deals with. So I believe it's called 14.7. It is. So this is going to be section 14.7. Okay. Badly drawn picture, but here goes. Can you imagine a badly drawn picture, version 2? There, okay. Can you imagine a surface that looks a bit like a bowl? In the 3D world, wouldn't that point be called a local minimum? Great. Can you imagine a surface that looked like an upside down bowl? Wouldn't this point here, wouldn't it be reasonable to call that a local maximum? Isn't that analogous to Calc 1? Find the local max and find the local min of f of x equals x cubed, right? That kind of question. Right? And so that's a local max, and that's what a local min looks like in a 3D surface. We're talking only 3D surfaces here, right? Local max, local min. So far, so good. So what on earth is the third thing? A saddle point. Here goes. Now, you might be looking at that, and it's because I don't draw very well, that's a local minimum, which it is from this perspective. But can you imagine you're looking at from that perspective? Isn't this a local max? So you imagine slicing the shape parallel to the x-axis, you would be seeing a whole load of hills, wouldn't you? And that would be the top of a hill. But if you slice it with the y-axis in mind, can you see that that then would be a local minimum? So in the 3D world, there are three possibilities. What would that look like in the 2D world? Well, in the 2D world, couldn't you have a minimum? Couldn't you have a maximum? And couldn't you get one of the funny little horizontal point of inflections? Now, I know that shape doesn't look like that. It's not meant to, but the analogy is, isn't there three things that can happen in Calc 1? Well, now there's three things that can happen in Calc 4. And our job is, if I tell you the equation of a surface, like I tell you the equation of a curve, can you find where these points are? That's the first goal. And then once you find out where these points are, can you then tell me if it's a local max or a local min? Right? Or a saddle point. And that's where we're going to deal, or that's how we're going to deal with it. So there's going to be a kind of shopping list of how you go about that. So, time like, yeah, I got time. So, got my little notes here. First thing you're going to do is you're going to find the critical points of the function. Basically, it's a surface. F of xy. Now, how do you find the critical points? The critical points occur when the partial derivative with x is the same value as the partial derivative y, and they are both equal to 0. So if I bring back my little picture, can you imagine slicing this shape parallel to the x-axis and then slicing this shape parallel to the y-axis? Would you agree that in both those orientations, won't the derivative be horizontal? It will be 0. Right? The partial derivative with x will be 0. The partial derivative of y will be 0. Now that means that we have more algebra to do than we used to. And back in the Calc 1 world, didn't you just find out when the first derivative was 0? And that told you where to go looking. That's the first thing in our shopping list. Second thing in our shopping list is you calculate d. And d is the second derivative with respect to x multiplied by the second derivative with respect to y, take away the second derivative xy squared. And it's just magic. We just tell you that's how you get d. If you're interested, it comes from the determinant of a 2x2 Jacobian. And if you're not interested, it's magic, and this is d, right? So you calculate this at the critical points. And then the third stage. If d, this guy, if this guy is greater than 0 and the second partial derivative with respect to x is greater than 0, if both of those are true, then you are looking at a local minimum. If d is greater than 0 and the second partial derivative is negative, then you're looking at a local maximum. So that's how you tell whether you've got a hill or a valley. The d will be positive in both cases, but the second derivative with respect to x will be positive, and you'll have a min and it'll be negative if you've got a max. Can you remember in Calc 1 a test, because that's basically what we're doing here, a test, called the second derivative test? And didn't the second derivative test say if the second derivative is positive, you have a minimum, and if the second derivative is negative, you have a maximum? You remember that guy called the second derivative test? This is analogous to this. Now, what's the third thing that can happen? Well, if d is negative, so you calculate this and it ends up being a negative number, then what you can say is that it's not a local max or minimum. That's really all you can say for sure. Now, it's probably a saddle point. Probably a saddle point. But you'll need to check it. Using software. So if the if at the critical points the value of d is a negative number like -10 or -2, then the only thing you can say for sure right now is that it's not a local max or min. It's definitely not these two guys. It's probably going to be a saddle point, but to be really sure, what you do is you plug it into, you know, that 3D software we haven't used since week 1. You plug it into that and you look at it, and if you see one of those shapes at the point you're interested, it's a saddle point. And if you don't, then basically there's nothing, you know, just move on. There's nothing of interest to see here.
Real quick, if a saddle point is just like a local max and min at the same time,
Correct.
why does that occur when d is, or why does that not occur when d is less than 0?
It does occur when d is less than 0.
Okay, yeah.
But other things also might happen. Right. The only thing you can say for sure, unless you go into it deeper, is that it isn't a max or a min. If d is less than 0, it's not a max or a min. That's the only thing you can check. What you then have to do is just look at the thing. Just go to a bit of software and say, oh, is that what you look like at 0.12? I see a saddle point there. Then you know it's a saddle point. If you look at your shape at 0.12 and you say, I can't see anything going on, then nothing's going on. The chances are, very strong chance that it will be a saddle point, but you know, there's some weird shapes in the world, so you can't be 100% sure. So you have to look. Does that make sense?
Yeah.
Okay. So let's do one. Let's pick. So while you're all saying hi, we're going to do the same question again, but this one is straight out of the textbook. Only this time the numbers are going to come out really nice. Partial derivative with respect to x is 2x plus y. Partial derivative with respect to y is x plus 2y plus 8. Double check that. 2x, y, nothing. With respect to y, nothing. X, 2y, and 8. We got it. There's my two equations. Oh, equals 0. All right. Would you agree that equation 1 looks probably the best candidate, and I should be able to write y in terms of x? Right. So I will do that. So if you take equation 1, if you rearrange it, can I just do that in my head? Would you agree that y equals 2x? Negative 2x. Now, if I put that into 2, what do I get? I get an x plus 2y plus a equals 0. I get an x, add 2 lots of this guy, plus a equals 0. I get negative 3x plus a equals 0. So, well, I was hoping for nicer than that. But it's doable. Would you agree in this particular case, there's only one critical number? And the coordinates of that critical number are an x coordinate of 8/3. And won't the y coordinate be negative 2 this guy? So that will be negative 16/3. That's the only critical number I've got. Guess I should call it critical point. It's the same thing. So phase 2, I need to calculate D. So that means the second derivative with respect to x times the second derivative with respect to y. Take away that second derivative squared. Okay, I've got the guys here, so I'm just going to do it right out the bat. The second derivative with respect to x is 2. The second derivative with respect to y is also 2. If you take this guy and you differentiate it with respect to y, you get 1 squared. Would you agree that in this case, well, you get 3? Would you agree it's positive? Now, in this particular question, the original function was so simple that wasn't the second derivative just numbers. But can you imagine if this was x cubed, this might be 2x and that might be 2y plus z, or stuff like that, in which case these numbers would get used. Now, I still need to know what the second derivative with respect to x is, and unfortunately for this question, it's just a number. Oh, by the way, isn't this number also positive? According to our hit list, what situation do you have when D is positive and the second derivative with respect to x is also positive?
Local min.
You have a local min. So we have a local min at 8/3, comma, negative 16/3. I think tomorrow I'm going to go looking for a question which is harder than this one, but with nicer solutions, and definitely not as hard as the first one, which just had some really ugly solutions. So there should be a sweet point where there's at least some x's and y's here, right? Something you can get your hand, get your teeth into. I don't know what this shape is. I wonder, I'm going to try. I know it's about 1 minute and I might screw up, but I'm just curious. I'm going to go into our website thingy, or Canvas site, and with a bit of luck, darn, it's being slow today. I'll put this function in and we'll see what we get. Okay, so here we go. You can't see it yet, but I'm typing it, or I will be right now. So it's going to be, oops, here we go. Z equals x squared plus xy plus y squared and plus 8y. Oh, got it. Okay, you're now about to see what I can see. We decided this was a local minimum, didn't we? That's what the math told us. That's what that shape looks like. Do you see at that point, oops, at that point there, I bet you that point there has an x coordinate of 2/3 and a y coordinate of -16/3. I should actually find its z coordinate, I just forgot to, but couldn't you go back to the original function and plug in the x's and y's and get the z coordinate at that point? So the method has successfully said there's only one critical number, there's only one thing happening with this surface, and that it was a minimum, and we told you where it was, which is pretty cool. If I rotate this, we might actually see its location. Can you see that it is located roughly about here? And I'm assuming that's 8/3, -16/3. What's that, about 2 and a bit, -5 and a bit? Could be. No. Yeah, could well be. And that is us for today. So have a nice day, everybody. I shall see you all tomorrow, where we get to play about with some more of these guys.
Thank you.
You're welcome.
Thanks.
Have a good day.
You too.
See you tomorrow. Take care.
See you tomorrow.